So we were seeing about the different stability analysis techniques for feedback networks. So we have stopped with gain margin and phase margin. So today we'll start with root locus technique. So the, just need to understand the logic about how to draw root locus. We will not get problems in the exam for root locus. So one obvious method which is going to involve the transfer function for checking the stability is going to be root locus method. So we are going to take a transfer function. It is called as closed loop transfer function, and we are going to solve the roots of denominator for getting the poles. We are going to locate the poles and zeros, and we are going to vary the frequency and see what is the path taken by the trajectory. So this method will help us to clearly sketch how the poles are going to move as we are going to vary the parameters of the transfer function. So to understand how a root locus works, so we'll take the transfer function denominator. It is going to be of the form 1 plus a of s into f of s. So I'm going to equate that to 0 to find the poles. So p of s equal to 1 plus a of s, f of s is equal to 0. So if we equate, you get a of s into f of s equal to -1. So I'm going to write this into magnitude angle format. So magnitude of a of s, f of s will be 1, and angle of a of f, f of s will be odd multiples of 180, because -1 can be any angle which is odd multiples of 180. So I write 2n plus 1 into 180 degrees. So there are some rules how to draw root locus technique. So we are going to see each rule how to draw the actual root locus technique. So first rule one is always the root locus will start at the poles and it will end at the zeros. So the starting point is going to be the poles and ending point is going to be the zeros of the transfer function. Okay. So for that, first we need to know how to find poles and zeros. As you know, in the transfer function, if you equate the numerator to 0, you get the zeros. And if you equate denominator of the transfer function to 0, we get the poles. So first we have to locate the poles and zeros of the transfer function. So suppose we express a of s into k of s as k into g of s, some constant into the gain function. So we can vary the value of k and we can plot how this a of s into f of s is going to vary. So this k will represent the gain factor. Okay, so in this case, the mandatory condition may be stated as mod g of s equal to 1 by k. So we can take this as a testing condition and we can plot the root locus technique. So when it is very clear that when the g of s is very large, k value will be small and it is going to be vice versa. Okay, so hence the different values of s that satisfy the condition are evidently or near the poles of the g of s. So definitely for the first step in root locus is going to be identifying the poles and zeros and plotting them. Similarly, when the value k is going to be large, g of s will be small. So definitely it is going to end near the zeros. Okay, that is why we are going to take the condition g of s equal to 1 by k. G of s and k are inversely related. So when the value of g of s is large, we say that it is going to denote the poles. When the value of g of s is going to be very very small, it is going to denote the zero. So that is this rule is stating that the root locus will start at pole and it is going to end at zero. That is rule number one. So now rule number two is, if a root locus branch lies on real axis, it resides to the left of the odd number of left hand side poles plus zeros and to the right of the odd number of right hand poles plus zeros. So this is just a statement. This will not be clear, but if we see the mathematical implication of that, we can understand that easily. So you know that if you want to first, you have to find the pole. So 1 plus k into g of s equal to 0. So g of s will be a negative number. So k into g of s will be equal to -1, or g of s will be equal to -1 by k. So assume that g of s is going to have so many number of zeros and poles. In the numerator, you can see I is equal to 1 to z. Z is the number of poles. Denominator, you can see k is equal to 1 to p. P is going to be the number of poles. So the numerator, I'm going to have zeros. Denominator, I'm going to have the poles of the transfer function.